MakeReal specialises in creating immersive learning solutions across a range of technologies. To download their latest academic paper on how to turn learners into activists, visit makereal.co.uk/activists.
Hello, I'm Kate Fitzgerald from the Learning Hack team, welcoming you to a new episode of Great Minds on Learning. In this highly acclaimed series, Professor Donald Clark, internationally famous author, blogger and entrepreneur, joins John Helmer to explore 2,500 years of thought and theorising about learning from the Greeks to the geeks. This time we explore the roots of AI learning. Once the stuff of science fiction, artificial intelligence is now a part of everyday life. But the story of how it came into being and the vital role played by researchers who probe the way we think and learn is not often told.
Welcome to this episode of Great Minds on Learning, the first in a new season, our fourth in fact. I'm here with Professor Donald Clark, my mentor and guide in this journey along the highways and byways of learning theory as I stumble along in his wake, uncomprehending. This time we're tackling artificial intelligence and learning, and I think I may do a fair bit of stumbling here because artificial intelligence really is a bit mathsy, but there are few people more qualified to open this subject up for us than Donald. He literally wrote the book. He's written a book called AI and Learning, link in show notes. He does it himself. He has a company that creates AI learning, and he was witness to some of its early developments at Dartmouth College in the last century, which I'll leave it to him to tell you about. First, Donald, there's an important question that needs to be settled. After an online seminar you participated in recently, which I watched, very good, run by a friend of the podcast, Leonard Hooks, someone tweeted, "I am worried that Donald Clark has transmuted to become some kind of AI deity. Was he really there? Were we just listening to a Donald Chat GPT bot? We need to know the truth." So, Donald, do we need to give you a Turing test? Can you prove you're you and not some AI-generated deep fake?
Well, a lot of people put that on Twitter, and it happened by accident, actually. My camera wasn't working on Zoom. So they heard this sort of spectral voice coming out of the darkness, for a full hour, as it were. But actually, there was a very interesting real example which was related to podcasts, because I don't know if you noticed that you saw that recently, it was just a couple of weeks ago. Yep. Joe Rogan and Steve Jobs, who's no longer with us, of course, did a completely AI-generated podcast. Everything was generated using AI. Now, the crazy thing about this podcast, which I've listened to, is at the beginning it's a bit clunky and so on, but then suddenly it gets quite good. And then suddenly you find yourself forgetting that Steve Jobs is actually dead. Yeah. And it seems like a real conversation. So I think the podcast, it sort of blew my mind, really, but the way in which we can be drawn in, we think that things produced by AI are actually real human beings. It's almost a Turing test thing, but I really advise anybody to look that up and have a listen. Try and get through the first 5-10 minutes. It's about 20 minutes long, because the second half is absolutely astonishing. They go into a lot of detail about real products. At one point, Steve Jobs, I remember it stuck in my mind, actually, he says that he compared Adobe's products. This is Steve Jobs. He used the analogy of a car where you have to buy all four wheels separately and then assemble your own car, which was a brilliant answer, but completely generated by the AI. Quite a creative response in many ways, and typical of the thing that Steve Jobs would have said, and in his voice. So they've sampled the voice.
Not Michael Fassbender's voice.
No.
Yeah. Okay, so can you introduce us to this group of theorists we're covering this time? Sad confession, I hadn't heard of any of them. And I note the absence of several people I have heard of, such as Marvin Minsky, Kurzweil, Nick Bolton, and so on. I'm sure Minsky has a bit part in this episode. I'm sure there's good reasons for those exclusions, but tell us about the ones who made the cut.
Yeah, so to think about the proposition that we're tackling today, John, we have neuroscience, as it were, looking at the brain, looking at neurons, and then we have artificial intelligence with all that language about neural networks, layered neural networks. And right now, as we speak, that's gone crazy on the internet, almost a global meme, the whole ChatGPT thing. So this has landed in people's laps. They suddenly see how amazing it is, and at the same time, they're getting a bit scared by it because it's incredibly powerful. Now, it hasn't surprised me because I was working with GTP way back when it was first released, and that was a couple of years ago. And indeed, I spent a long time, and as you know, in the AI thing, when I was at Dartmouth, that's an Ivy League college in the US, they weren't actually doing it. It's famous because in 1956, which was the year of my birth, they had the famous AI conference with John McCarthy. It's where the term artificial intelligence was coined or invented, and some amazing stuff was done there. And then all my life, I've been interested in it. In the 1990s with Clive Shepherd, we did an intelligent tutoring program using very primitive hardware and software at the time, and nearly killed us. But that was a learning program using AI, what was then called intelligent tutoring. And then more recently at Learning Pool, as a director, we sold Learning Pool quite recently, 2021, for $200 million. And that's because we had built a sort of AI learning company, really, there. And that was an astonishing achievement, I think, because it was a more traditional LMS, content authoring language type company. But as soon as we supercharged the company with the sort of smart platform, LXP, AI, data, learning record store stuff, then it went through the roof, and we won one of the biggest training contracts in the world on the back of that. And I have my own company, of course, doing the consultancy and content builds. So I've invested in it, written a book in it, blogged about it, traveled the world speaking about it, and so on. But I think these people are dear to my heart because it's an untold story here. So I'm going to start with a neuroscientist, and that's Eric Kandel, who is a neuroscientist, and actually a neuroscientist who has a Nobel Prize. One would think that the learning community might know somebody because he's probably the only person, other than Daniel Kahneman, perhaps, has a Nobel Prize in this field, but nobody has heard of him. But he studied learning in a neuroscientist sort of way and got the Nobel Prize for it. So we'll look at the neuroscientist bit first, and then we'll look at the other side. So when we're comparing, let's say, neurons to neural networks, we have this amazing history from Hebb through McCulloch and Pitts and Rosenblatt. These people are all dead now. This is, we're talking about going back across the whole of the 20th century, really. It took these amazing brains to come up with these amazing artificial artifacts that reflected the brain. And then more recently, we'll look at Rumelhart, Hinton, and LeCun. I mean, some of these names are, if you're in AI, they are the gods of AI, as it were, not only for the theoretical but practical work. And then Hassabis, who's the chief exec of DeepMind in London, but really the beating heart of Google. So this is an untold but fascinating story, I think.
So let's get on with the story. First of all, Eric Kandel, 1929, he was born, still among us. Eric Richard Kandel is an Austrian-born American medical doctor. And it's a theme with these people, isn't it? That there's a kind of, it's the grey squidgy stuff as well as the psychology stuff.
Yeah.
He specialised in psychiatry, a neuroscientist and a professor of biochemistry and biophysics at the College of Physicians and Surgeons at Columbia University. He was a recipient of the 2000 Nobel Prize in Physiology or Medicine, as you said, for his research on the physiological basis of memory storage in neurons. Yeah. More important stuff for this episode. He was born in 1929 in Vienna. His mother was Ashkenazi Jewish from what is now the Ukraine, very much disputed territory as we were recording. And the family fled persecution by the Nazis and moved to Brooklyn, USA, just for the Second World War. I mean, that's another thing. That diaspora is such a theme of this series of great minds. At Harvard, his major was history and literature, but he became interested in learning and memory. Psychology at Harvard at that point was dominated by B.F. Skinner, who we've covered in a previous episode, but people will have heard of anyway. But Kandel's work is very different from Skinner's. It's essentially centered on an explanation of the relationship between psychology and neurology. As you'll probably tell us, Skinner wasn't interested in any of those things. He thought the mind was a black box. This might lead to think of us perhaps as a cognitivist, but really his work on neuroscience and learning points forward to a 21st century preoccupations. Neuroscience is very big since turn of the millennium. But Donald, what is his relevance to artificial intelligence?
Yeah, well, he gets this Nobel Prize for his work, not on the human brain, which is important here, but on a thing called a sea snail or a sea slug called Aplysia californica. It's about 1.5 feet long. It's a sort of horrible, spongy, sluggish type creature with tentacles coming off it. It looks very strange, in fact. But it's a creature that is worth studying because it has about 20,000 neurons. And that's enough to make it a sort of active, proactive learning creature, but enough that's manageable to study in a lab. Okay, so it's got these neurons are up. The neurons in this creature are up to about 1 millimeter in length, so they're really quite long and big. So he did a lot of very detailed lab work using that particular creature. He's neither a cognitive nor a behavioral science, really. He's what you would call a neurobiologist or a neuroscientist. He's looking for insights primarily into learning and memory being the big thing here. So his insight, to jump to the conclusions for a minute, so he was the first person that recognized that the functional and biochemical features of nerves and synapses in things like snails and worms and flies, he also used the Drosophila fruit flies, are not substantially different from we mammals and humans, okay? So you can perhaps draw conclusions from those structures to our brains because we evolved along from that type of creature, okay? So he's working on these giant marine slugs or snails and had a focus on memory. You know, how we, first of all, procedural memories, and that's how the slug actually fears prey or reacts to prey, finds food at the bottom of the ocean off the Californian coast where they live. But he then moves also into explicit or declarative memory, the sort of facts and events that one can recall, you know, and plan off into the future. And his finding here is that sort of long-term storage, what we call long-term memory, involves gene activation, the creation of there's new proteins and new synaptic connections. He actually discovers this in the lab. He finds that memories are actually changes or the creation of new proteins and synaptic connections. Now, that second half is really important here, because when we come to Hebb and all these other people, they pick up on this idea. It was already known in a sense by the time Kandel comes along here, but they pick up on that idea. But it's foundational here that Kandel finds this link between experience of the world and biology and the neural structure of the brain. Learning can now be seen as experience captured as cellular change. And he does that. You know, he discovers that. That may seem trivial, but nobody had come up with this before. Nobody had actually found out how memories were actually being stored in the brain. And then he goes on to look at the plasticity of a brain, how it might change in many ways, okay, with molecular modifications. It's quite clear to me that the brain is a material object and that there has to be, we now know that it's a mixture of synaptic communications, a mixture of the chemical communications and the physical or the electrical communications across the brain, in terms of consolidation and reconsolidation of memories. So sorry that was long-winded, but he did a lot here, and he's just an amazing guy, and the fact that he did get the Nobel Prize is the big stamp of approval on his discoveries.
Okay, we've got rather a lot of people this episode, so we could talk more about Kandel, but I think it's probably an idea if we move on.
Yeah, sure.
Now, the next person we're looking at is Donald Olding Hebb, 1904 to 1985, a Canadian psychologist who was influential in the area of neuropsychology, where he sought to understand how the function of neurons contributed to psychological processes such as learning. His parents were both medical doctors, and his mother, who was influenced by the ideas of Maria Montessori, homeschooled him until the age of 8. After that, later on, he studied at McGill and Harvard. He's best known for his theory of Hebbian learning, which he introduced in his classic 1949 work, The Organization of Behavior. He's been described as the father of neuropsychology and neural networks, That's an important term, neural networks, occurring here for the first time. Also, and here's a first, I think, for Great Minds on Learning, he was a headmaster, which presumably gave him the opportunity to try out his theories experimentally on beings other than rats.
It was so important that you mentioned that the fact that he was a teacher and a headmaster in Montreal, John, because his inspiration for this was his experience with learners or the students he was teaching. And he came at this problem understanding that learning has very little to do with teaching. You know, you can teach good learning strategies and create the right environment for people to learn, but actually, ultimately, it comes down to the person and their motivation and their ability to learn. It all comes from the learner. Okay, so how does that happen in this thing called the brain? So the brain, or what is the physical nature of learning in the brain? Hebb really tackles this big time. Okay, and he comes up. If you imagine all these neurons in the brain, the little things sticking off the side of them, and they connect with other neurons. Now, we now know, that Hebb didn't know this, we now know that it's not electrical connections that connect neurons, so that's part of the story. It's actually a chemical process, but put that to one side for the moment. The Hebbian discovery is famously described by just 6 words. Neurons that fire together, wire together. In other words, when we take that idea that Kandel had, is how do we take experience and apply it to biology? If we have an experience and the neurons in our brain fire together, or in what Hebb called cell assemblies, we now call neural groups or whatever, they fire together and then they wire together. In other words, the Hebbian learning is that process of association. When you use your brain, it starts to store stuff as memories. It's like a muscle in that sense, but not literally. Okay. Now, actually, there's a much more detailed level of this, because down at the cellular level, stick with me for a minute here, it gets a wee bit more complex. When the axon of one cell, the bit that communicates with the next, is near enough to another cell, let's call that this sort of cell B, to excite it. So one cell A, it excites through its axon cell B, okay? And it starts to repeatedly fire off towards cell B. Some growth or change, metabolic change, takes place in both cells. So when cell A fires, it affects cell B, and both benefit from that, okay? So the A's efficiency, as one of the cell that fired B, is increased. So simply the firing or communication is a process by which the brain learns. Okay, I don't know if that was clear, but neurons that start to fire together, wire together, hence we learn. It sounds, well, that sounds right to us, but nobody knew this before, you know? That's what Hebbian learning is. Okay, so it's a sort of physiological psychology, if you want, how the brain actually does this. So, and it's the first theory that really comes up with an actual mechanism for learning here, or the encoding of knowledge and memories in the brain, to be more specific there.
Yeah.
He widens that out and says, well, this happens in the brain all the time, not by individual neurons, but by cell assemblies, you know, groups of these things. He then took a leap of the imagination, this is more speculative, and thought that ideas were really what he called phase sequences. Now, there's whole numbers of these things firing and therefore wiring together. And this is sort of basically true in a way, because the brain, as we now know, is a highly distributed process. When you take an MRI scan or whatever, any form of scan in the brain, when we're thinking, it's not some little localized path like walking through the forest that sparks across the brain, but a massively sort of distributed process. Some of it's localized, but it's quite widely distributed. This wiring really and firing really does take place when you have the scans that Hebb never had when he looked at this problem. Now, there's a really interesting conclusion that Hebb came to from this, which is why I really admire him so much. He thought that once you understand this is true, how does it affect learning and learning theory, which is what our podcast series is about? And actually, what he says is you should expose children and yourself as an adult to as many experiences as possible. Just get that firing and wiring going, guys. You know, let's get going with this. And he didn't believe in very narrow cast curricula. or limiting children's experience. He thought that that's what you should be doing with kids. You should be opening up young minds to new ideas and new experiences, not a closing of the mind, but an opening the mind up. And, sadly, I don't think that's necessarily true of the educational system. I think there's a lot of closing young minds down as opposed to opening young minds up in that system with a very strict and narrow curriculum.
Mm.
I mean, it's mostly a theoretical curriculum for a start, with no practical knowledge or vocational knowledge whatsoever, which is bizarre.
It's interesting as well that you say that you can't actually teach, that it has come from the learner. Quite recently, the UK government has decided that everybody should be mandated to learn maths to the age of 18.
Yes.
Regardless of what they're interested in, which feels odd.
Yeah, well, every time some public school boy becomes prime minister, we get up some sort of daft idea like this. Well, it was Latin. I remember that. God, I wrote tons on that, debated it at the British Museum, the madness of that idea. I mean, that's recognised as just idiotic now. But now it's maths because it's Richie Sunak and he's an economist by background. This is just the arrogance of the private school system, really, I think, in the end of the day. And no doubt it will be some other thing coming along here, but the idea is plainly absurd. Let's leave it at that.
On that point, let's move on.
Yeah, actually, there might be one other thing that's mentioned with Hebb, because there was. I think it's a balance here. There's that dark side to Hebb's as well.
Oh yes, the torture.
Well, that's right. The American government realised that he was onto something here, and at the same time, this was the Cold War. We suddenly had all these confessions by American spies in Russia and others. And the American psychologists suddenly went, God, these Russians are onto something. How did they get these people to confess?
Yeah. Manchurian Candidate and all that stuff.
Yeah, that's right. And the Russians had struck upon something which Hebb's had studied in detail, and he took his work, in fact, on sensory deprivation. And Hebb's, to be fair, had used student volunteers. It wasn't sort of, torture in that sense.
Yeah.
But the CIA has now subsequently found through declassified documents, funded a lot of research in this area. And the Americans, sadly, I think through to Guantanamo and waterboarding, actually started to do this. And it all came out of the Cold War, but let's not pretend that it's gone away. But I wouldn't blame Hebb's for this. He's long dead, as it were. But let's not pretend that there can be a dark side to discovering how to manipulate the brain.
We hope this podcast ups your knowledge about learning. But did you know learning podcasts, that's audio training created according to evidence-based principles, is a powerful and fast-growing medium? Assemble U is an audio-first provider with a ready-built course library to help your people improve productivity, leadership, well-being, and more in their downtime. Assemble U also creates audio courses unique to your company or institution. Try it free today at assembleu.com/greatminds, all one word. So moving on, Warren Sturgis McCulloch, 1898 to 1969, and Walter Pitts, 1923 to 1969. They died in the same year. Yeah. McCulloch was an American neurophysiologist and cybernetician, born in New Jersey, like Bruce Springsteen, and originally destined for the Christian ministry, unlike Bruce Springsteen. Studied at Yale and Columbia, qualified as an MD, again, and worked at a hospital for the insane. Later was a professor of psychiatry at the University of Illinois at Chicago, and then MIT. And he's most famous for the results of his work with Walter Pitts, the other part of this twofer. Pitts, very different character, was a logician and mathematician who worked in the field of computational neuroscience. Born in the Motor City, Detroit, he was an autodidact and a prodigy, and from a family that gave not two figs for learning, it seems, and considered him a freak. At the age of 12, over 3 days in a library, he read Bertram Russell's Principia Mathematica, then wrote to Russell a letter telling him where he'd gone wrong. Russell was so impressed and taken up with his analysis, he offered him a place at Cambridge at the age of 12, which Pitts, perhaps unsurprisingly, didn't take up. At 15, having kept up his correspondence with Russell, he ran away from home and his awful family to Chicago, where Russell was a visiting lecturer and attended those lectures. And then he continued to hang around at the University of Illinois in Chicago. And it was there he got together with McCulloch eventually, who took him in. because he was homeless at the time and not officially registered with the university. He had some kind of menial job someone had found for him there, rather than actually being registered as a student. He was an unusual person. We'd call him neurodiverse nowadays, I think. He refused to sign his name on anything, didn't even want his name to be attached to his work. Nevertheless, together with McCulloch, he authored 2 absolutely groundbreaking foundational papers. Donald, this stuff gets pretty complicated, and your mission impossible, should you accept it, is to explain their breakthrough in terms that even a humble English graduate can understand.
Yes, now we're getting to the heart of the matter, because these 2 extremely bright people, so McCulloch, Pitts especially, was clearly a genius.
Yeah.
But they were the first to create this link, or create a mathematical model of a neuron. That sounds trivial, but it was a massive task. And it was inspired by the concept of a biological neuron. So this is where we get to this comparison between the biological brain and how we can build something similar to, or be inspired by, the neural structure to give us artificial intelligence. This is the beginning of this journey. And we have to be careful here. Just because the word neuron sounds like neural network doesn't mean to say they're the same thing. Mm-hmm. But one did inspire them. It's a bit like flying. We didn't learn to fly by studying the flapping of wings of a bird. We invented another form of technology that did it more efficiently using thrust and engines. So it's inspired by, but not the same. Okay. Now, to get down to the detail here, they start with what we know about the brain. So we know we have these neurons, we know that they're networked, we know that they communicate with each other, the whole Hebbian learning story. That we know is true. Okay, so what these 2 guys come up, and they call them neural networks, or they call them nets, actually. Originally, that was the term they used. So if you take one of these individual neurons, they have soma and axons. So the synapses, the spaces between these cells that communicate with each other, between the axon of one and the soma of another, a bit like 2 aerials, one on each, if you want to call it that. At any moment, every neuron has a sort of threshold. It's a bit like listening to your television. You can't actually hear anything on the volume button until it passes a threshold where your ears can suddenly hear it. So every neuron has this threshold. And now that has to be exceeded by excitation to initiate an impulse and communicate with the next neuron. Now, their breakthrough, a massive breakthrough, was to represent all this in propositional logic or mathematics. So they're replicating what actually happens in the brain in mathematics. Okay. Yeah. Now, this goes back to Leibniz. This had been speculated upon, of course, before, Leibniz himself thought that you could create whole propositions in the real world using this explanation. But let's not go too much into the history of this. Now, what you've got here is these neurons get the preferences or synapses that come across in this model to produce an output, but it's a binary output. It's just switching on or off, okay? So the input into the whole process is 2 types. You can either excite a new cell or inhibit it, switch it on or off. That's what I mean by binary outputs. Okay. Now, what they do, that's quite simple. It's either on or off. That's the whole basis of modern computing. But they introduce another layer of complexity in here, which is why it's propositional logic, really. They introduce Boolean functions. Now, these are words like and. So Donald is Scottish and British. Okay, that's an and function. Or Donald is male or female. What is he? That or function. Then there's the not function. So and, or, and not. These are 3 logical operators. Mm-hmm. And what these 2 guys did, amazingly, was represent that in mathematics. And I was speculating, not necessarily that the brain does it this way, but they have things called linear threshold gates, LTGs, which mimic what they think the brain does. So they have these things called logic gates, which are mechanisms in computers that they think mimic how the brain works. They have and gates. That's when all the inputs are on. So X and Y, all inputs on. There are OR gates where only one input is on. So it's either X or Y, only one of those things. That's what OR means.
Mm.
And the neuron switches on when the threshold is passed. You know, that's what makes thought happen. And memories are created by that. Then you have not gates. Now, that's the inhibitory work in synapse. That's holding some back, going, hold on, let's not do that. Okay? So, and, or, and not, the logic of all that can produce lots of very sophisticated ideas and real thinking. Okay? Now, at this stage, remember, this is not about learning. This is just about the mechanism or the gates and the ways in which the brain could work represented in mathematics.
Yeah.
Now, they took one other step. Sorry if this gets a bit esoteric, this really, but they took one other step, which is amazing at the time. It was 1947, and went to universals. So universals are general terms about the world. You have individual examples of dogs and breeds of dogs, but then you have the general universal of the word dogs, meaning all dogs. Mm. They thought that they came up with a mechanism for the explanation that all swans are white, universals, again, using the mechanisms of mathematics. They do that a bit later in another paper. But the original paper, the paper that you alluded to at the beginning, which is called a logical calculus of ideas or something in nervous activity. And that was in 1943.
43, yeah.
Yeah. This had a profound effect on computer science. Really profound effect. It gave us the opening gambit of a process that would take the rest of the century to complete. But at the end of that process, we have ChatGPT and something that blows our minds.
Yeah, there's so much in this that kind of made me think. I mean, that last thing you talked about, universals, threw you back to Plato and the forms.
Yeah.
You know, Plato and Aristotle and the Neoplatonists, this endless debate over forms that's kind of been a thing in philosophy. The thing about the threshold, that the voltage or whatever has to be of a certain limit to kind of get through to make the connection. Am I wrong in thinking that is a thing in the affective kind of domain of learning, something that Nick Shackleton-Jones makes a lot of, that you have to actually have to cross that threshold with an input in order to make it memorable in any way in the first place. In order, we can't learn anything if we don't care about it.
Indeed, yeah.
Yeah.
I mean, these guys were looking at straightforward propositional logic, which is the sort of mathematics of it. But the threshold thing certainly explains the affective or emotional thing that, that you can feel that rushing through the brain, jealousy, rage, anger, whatever it is, love.
Yeah.
It certainly has an explanatory thing there. Going back, and I think that's definitely true, but going back to the universals thing, you're right. One thing that really puzzled people about the brain is we can think of a circle, a Platonic circle, but we can think of different sizes of circles. We can see them shrinking. Right? The Gestalt psychologists, behaviorists, and most cognitive psychology didn't have an adequate explanation for this. And it's proved very difficult in artificial intelligence to cope with universals. You may say that the recent history of artificial intelligence has been coping with how do you identify dogness or catness, You've got lots of images of cats. How do we know it's a cat as opposed to something else, as opposed to, a dog, for example. Yeah. And that we'll come to that in a moment, actually, through perceptrons. It's a nice link here, but we start to make progress with the next stage.
Yeah. Can I have one more query about this? So, sorry to kind of lengthen the time of the podcast out, but I just found this so interesting. It does seem to me that this is, I don't think it's exaggerating to say that this is a major shock that is perhaps comparable to Darwin and what that did to religion, because what this basically says is that your thinking is maths. Thinking is maths. Yeah. People on the kind of art side of the two communities that C.P. Snow talked about are just outraged by this and continue to be outraged by it. And it's something that we're kind of working through and living through now, I think. It's the biggest shock, really, since Darwin, to the way people think about consciousness and themselves and communication and everything. Thinking is maths.
Yes, that's right. I mean, when I wrote my book on AI for learning here, I was really clear on what I personally think about this, and that this is second only to writing, probably, in terms of the technological revolutions we've had in the history of our species. but it's different from writing. Writing is just really us manifesting our ideas externally so we can share them with others. This is something way beyond that. This is us creating technology that is better than us, or can be better than us. And that's quite clearly happening in all sorts of individual small domains, whether it's playing checkers, chess, Go, computer games. AI can beat us hands down. But suddenly it comes along and produces, well, let's talk about just briefly chat GTP. GTP is an amazing thing, but it's not that amazing. It's just producing a lot of text. But let's think of the number of human beings on this planet who do that for a living.
Me?
You know, now we're getting quite close to it producing sort of report level text that's better than humans, or certainly the same as, or as good as. So if you're doing something that ChatGTP can be doing, should you be doing it at all? Really, it's a very good question. Yeah. And that shows how revolutionary this is.
I should ask ChatGPT to write the scripts for these and insert some stupid jokes. I'm sure it could manage it, actually.
Well, the thing about the interesting thing is there are whole areas of human endeavor, of course, that it can't do at all, like jokes. Well, yeah, it actually can do. There are a lot of joke generators and AI, lots of them, and they're quite good, actually. But they can't do this sort of fluid dialogue that we are having on this podcast, John. But it's getting there. That's the thing. Don't regard AI as some fixed entity. You know, GTP-2 was quite passable. It could write a poem it could take a poem by Wallace Stevens, and it did famously, and then produce a poem that we might think was written by Wallace Stevens, and human beings could not tell the difference. It was so good in terms of style. GTP-3, which we're dealing with now, is way beyond that. GTP-4, which is coming out this year, will be several orders of magnitude bigger and better. And so things are happening very, very fast here. But it was, for me, quite predictable, you know. When I wrote the book, you know, when you give talks at learning conferences and there's people just poo-poo, oh, it's never going to replace a teacher and so on. Suddenly that proposition is looking a bit dodgy. So I think it is a Darwinian paradigm shift. I've always thought that. I don't, and we're really merely at the beginning of this process. We're at this, you know, the 1859 Darwin stage where Origin of the Species has just been published, and we're suddenly seeing, we're going, holy shit, this is happening.
Let's dive back into the detail with our next theorist, Frank Rosenblatt, born 1928, died 1971, an American psychologist sometimes called the father of deep learning. Born in New Rochelle, New York, studied at Cornell, and then went on to the Cornell Aeronautical Laboratory in Buffalo, New York, where he was successively a research psychologist, senior psychologist, and eventually head of the cognitive systems section. Rosenblatt had wide-ranging research interest, and he also had a hinterland, which is what we say in the UK a lot, in other places as well, for what normal people would call a hobby. He had interests beyond his métier. He was active in liberal politics, for instance, and anti-Vietnam War protests. He was interested in astronomy to the point where he built an observatory on a hill behind his home to search for alien life. He died young in a tragic boating accident in 1971, not long after Marvin Minsky and Seymour Papert had attempted to rubbish the discovery for which he is most famous, perceptrons, as a result of which funding dried up for his particular branch of research for a while. Donald, those two were subsequently proved wrong, weren't they? But tell us about the perceptrons. What is a perceptron?
Right. So far, we've discussed the way in which McCulloch and Pitt described and or not typological mechanisms in the brain, okay, for making it happen, that sort of neural structure. We haven't come to learning yet. And what Frank Rosenblatt gives us is the concept of a neural network that can learn. Okay, so suddenly learning is on the table. And he thinks we learn by trial and error. Now, it's called a perceptron because his work was initially in the area of perception, okay, identifying objects in vision and speech, okay, that's really what he was after. And of course, we now know that computers can do that pretty well now. You know, we've transcended that. You know, I can speak to my Alexa in the corner. I had to spell it out in case you marks off. So all that stuff's come to pass. But what he does is actually build one. The perceptron is actually a real thing. It's actually in the Smithsonian Museum in the US. And what it is first of all, something that takes input is a grid of 20 by 20 photo cells, a little camera that makes up a 400 pixel image. Okay, if you imagine a little sort of grid like that takes light from the outside world or experiences. Okay, he builds that, but then there's a whole load of weightings. How do you actually learn? How do you make his machine learn? He had to do this using physical technology because the software was nowhere near as good at that time. You're talking about 1960s, early 1960s here. What he has are variable resistors that you find in old radios and so on that provide the weighted learning, and they're delivered by electric motors that turn physical dials on these resistors. It's a bit sort of Heath Robinson, really.
A bit steampunk, really.
Yes, it is. But of course, he was trying to do something that was incredibly difficult ahead of the technology because we didn't have the software or hardware to do it well. But this is why he's such an amazing character. His aim was to build essentially a learning algorithm, you want to call it that learns when you see things. So if you do something or see something or hear something, like identifying a cat or a dog or whatever, then the perceptron actually learns from its errors. Now, this is the important point. The perceptron is an error learning machine. Okay, so over time, it actually learns to recognize a cat, okay, because the shape of the cat, because it's constantly having an attempt to match what it knows with what it's seeing, it eventually learns what catness is. Now, as you rightly said, Marvin Minsky and Seymour Papert, that's another constructivism he came up with. I don't really much like those terms, connectivism, constructivism,
constructionism,
They're often confused and I don't think very helpful at times. He wrote a book called Perceptrons in 1969 that absolutely slammed Rosenblatt's theory. But who won out in the day? In a sense, Rosenblatt had the last laugh here because it's turned out that they were wrong. They had a point, actually, because how we were discussing those logical functions, and, or, and not. There is another logical function called XOR, and that's called the exclusive OR function. X or Y but type function. That's a more complex bit of logic, as it were. So now Minsky and Papert thought that the perceptron, as defined by Rosenblatt, could not solve the XOR problem. That was the basis of their critique, as it were. But actually, it came to pass that it was a solvable problem, okay? And unfortunately, Rosenblatt didn't live to see this. And the peculiar thing, he didn't live to see the really good research on his insights because he died in a boating accident, literally just after Minsky and Papert's book was published. I think it's a sad story here, really, because he got slammed by two people who turned out to be wrong. And he was left with that in his mind when he died. He didn't see the fruits of his labor come to pass. But of course, we have seen it come to pass. There's still people who think that the perceptron model has its limitations. And I think, that's true. But deep learning emerged from this one invention and has now become central in artificial intelligence. Rosenblatt's perception hasn't just succeeded and survived, it's become absolutely central to progress in AI. That's why he's such an important figure.
I think this is such an interesting story that's emerging here for people like me who haven't heard it in detail. It does get a bit detailed and kind of difficult to follow, but it's just brilliant.
Yeah.
So let's carry on. David Everett Rumelhart, 1942 to 2011, and Geoffrey Everest Hinton, born 1947, still among us. This is our next twofer. I like the word perceptron because it makes me think of 1960s science fiction shows on TV, like Doctor Who. We are the perceptrons. But I'm less attracted to the term we're going to encounter next, backpropagation. To be honest, it sounds a bit mucky. bit agricultural. But I'm sure after you've finished explaining it, Donald, it will be my new favourite word. So to whom do we owe this particular coinage? Let's find out. David Everett Rumelhart was an American psychologist who made many contributions to the formal analysis of human cognition, working primarily within the frameworks of mathematical psychology, symbolic artificial intelligence, and parallel distributed processing. Born in South Dakota, studied psychology and mathematics at the University of South Dakota and Stanford, taught at universities of California, San Diego, and Stanford. An illustrious academic career he had, with many awards, including a prestigious MacArthur Fellowship, the Genius Grant, sadly cut short by Pick's disease, a progressive neurodegenerative condition similar to what Stephen Hawkins suffered from, I think. Geoffrey Hinton, his partner, is a British-Canadian cognitive psychologist and computer scientist born in Wimbledon, where they do all the tennis, most noted for his work on artificial neural networks. Works for Google and the University of Toronto. In 2017, he co-founded and became the chief scientific advisor of the Vector Institute in Toronto. Rumelhart and Hinton were co-authors of a highly cited paper published in 1986 that popularized the backpropagation algorithm for training multi-layer neural networks. Okay, Donald, this is the bit where you make us all love that word, backpropagation.
Yes. Well, backpropagation is quite a complex mathematical idea as applied in artificial intelligence. And you mentioned two people so far, David Rumelhart, incredibly important, because he basically invents backpropagation. We'll come to what it is in a minute. Along with another guy called James McCulloch, James McCulloch, he also took that on board because it runs with another concept called parallel distributed processing. In other words, the idea that we have parallel processing across the brain and across neural networks as well, okay? This is relevant to the understanding of cognition, but it opens up the possibility of a model for neural processing. That's what and when I say neural processing, I mean in neural networks. That's what backpropagation is. You have David Rumelhart, then you have Geoffrey Everest, Hinton, and everybody in AI would know that name. You know, he's one of the gods of this world, as it were. He contributes massively to this. And another name I'll just throw in here, and that's Yann LeCun. He's a French AI genius, really. He's the chief AI scientist at Facebook, a professor at New York University. He's revered in the AI community as a pioneer of this work as well. So you have these three big names: Rumelhart, Geoffrey Hinton, Yann LeCun. And people in AI generally would know at least the latter two of those. So backpropagation. In this 1986 paper, Learning Representations by Backpropagating Errors. If there's one paper that really sort of acts as a springboard for modern AI, it's this paper. But it's incredibly difficult to explain what backpropagation is. But if I try by analogy here, if you imagine yourself climbing a hill, but you're blindfolded, and you might just feel forward with your foot, okay? So you're tapping away with your foot, and you find the point at which it's got the steepest ascent, okay? So you tap away, oh, that's the steepest bit, you take a step forward. Eventually, you will mathematically get to the top of the hill if you do that. Now, similarly, on the descent coming back down, you might feel around with your foot for the steepest step back down, and on you go. And mathematically, you will get to the bottom of the hill. Okay, so that is a gradient ascent, but it's also a gradient descent. Now, when you get these gradient descents in these perceptrons that we've been talking about, what you're doing is tweaking the weights as you go to lower the error rate. So this is all about, you may call it optimization.
Yeah.
Okay, so you're coming back, but you're lowering your error rate all the time until you get it right. You do it time and time and time again, layer by layer. That's why neural networks have layers. Okay. But there's a problem here. Supposing you're climbing a mountain with little peaks, and it's got a little peak, and then you start coming down again before you go back up again. That's what the XOR problem is in many ways. It's a logical problem that has to be solved. But in actual fact, backpropagation can solve that problem, as we've found. So this is a very sophisticated mathematical method, as it were, for optimization by calculating these sort of errors. What you might call the backward propagation of errors. That's why it's called backpropagation. Okay. And this is what, if you take these neural networks or the layered neural networks, this allows them to be trained. So if we take DeepMind, and AlphaGo, which beat, there are more moves in the game Go than there are atoms in the entire universe. But they had a system that they trained on Go until it was so good it beat the best Go player in the world. Now, there are many aspects of deep learning and neural networks, layered neural networks, that are doing amazing things, and they're largely based on back propagation. Not all of them. There's other forms of reinforcement learning and so on that are quite different. But what was interesting here, and this is what has given, it's particularly applicable in error-prone areas. So things like speech, which are really difficult to interpret or create, or image recognition. How do we know that's a cat as opposed to a duck or a dog? These are really tricky problems. But this is what this type of thinking and technical build, mathematical software build, has given us in AI, and it now can do all those things pretty well. Now, at the same time as the figures I've mentioned there, which is the Hinton, Rumelhart and Hinton, we had Jan LeCun, who also discovers backpropagation in France at exactly the same time. So it's worth mentioning him as well. Okay, there were, in fact, as we found, there's been all sorts of sources for this. But this ultimately gives us the sort of products we see in AI today that are blowing our socks off.
Yeah.
So the influence of backpropagation, neural networks and backpropagation, it sort of started with the recognition of simple words, and but it then moved into stock market prediction. We had huge success. My next door neighbor actually worked in that area and turned down a job at DeepMind, interestingly, because he getting so much money in this other area. Self-driving cars might be a good example. How do you calculate those? How do you optimize the recognition of a deer that jumps in front of the car, for example? That would be a good example. So this has been essential for progress in deep learning.
So it's about that kind of constant error correction, feedback loop feeding into refining the knowledge and learning and so on.
Yes,
have we moved away from? We started with a kind of exploration of how the brain works, how human brains work, the grey squidgy stuff. Now we're more talking about how computers can operate in machine learning. Right. Have we moved away from this, or are we still in a way working out? In other words, does the human brain do backpropagation, or is it just something that's useful if you're trying to program a computer?
Well, this is where we have to be very careful of sort of metaphorical thinking or anthropomorphizing here. It's not at all clear that the brain, and there's no evidence that the brain does backpropagation as such.
Okay.
But it may be a similar mechanism. It's certainly clear that we have to optimize things in real time to simply walk through a room. The brain is an evolved organ. We have a spatial sense, and we're doing it in real time so that we don't fall over, bump into things, and so on. And so clearly we do this process of optimization, and it must be doing it somehow. Now, there are those who believe in the computational model of the brain. I'm one of those people. I do believe that's true. That doesn't mean to say you believe in this backpropagation computational model. There's a sort of strong and weak form of computational models in the brain, and it's yet to be discovered, as it were, but I still think it's fundamentally mathematical and computational, and that we can find that out, how it works. And there are those who think that consciousness is the hard problem, that it's irreducible, people, and that you can't really solve that problem. That's more of a philosophical problem.
At the moment,
we have to be careful here in imagining that, and jumping to the conclusion, which was behind your question, John, that the brain thinks this way. There is no evidence for that.
Yeah, I mean,
it may be doing this in an entirely different way because it's a biological substrate using, for example, chemical communications between neurons. Now, that doesn't exist at all in the computing world. But interesting thing you can draw from this, it may be that the severe limitations of our brains, the chemical basis of neural transmission, is its big drawback, and the fact that we're limited to this little thing that has to be packed inside our skull, because the computation or computers can have very large memories, huge memories, in fact, which is what ChatGPT is based on or is trained on and draws upon. It has a digital memory that is right. It doesn't get confused, whereas our brains age and indeed we die, whereas you can have permanently stored digital memories. We have very poor working memories, for example, which is an evolutionary advantage, but it doesn't necessarily have an advantage when you're doing advanced mathematics, for example. So let's not imagine that the human brain is something we should be aspiring to here. What AI is doing is transcending many of those features of the human brain.
Yeah, I think what I wanted to say was that since we've been looking at these questions from the cognitivists onwards, there's been this sort of comparison of the human brain and the computer, which is very useful in working out how, long-term, short-term memory worked in terms of storage. And we've been talking about it a lot today as well. But it now seems that that kind of metaphorical connection between brain and machine causes as many problems as it solves, especially for the public understanding.
Yeah, I think it's a dialectic, John. We'll come to Demis Hassabis, where there's a very clear example of somebody who studies cognition in the brain, the hippocampus, and then builds DeepMind, which changes AI forever. There's a dialectic here, and that some people have been inspired, like Hebb's and so on, by the structure of the brain to create a theory. And then, of course, we have the perceptron, which is a physical model of neurotransmission. There are some people who've taken the inspiration of the brain into AI, but there's also inspiration going the other way as well, and speculation that maybe this AI stuff is uncovering how we actually think as well. That's more in the Bayesian side. So you have people who believe that our brains are predictive engines, and that actually they have to be like that in order to simply walk through a room. You have to try and be forwardly thinking or predicting what's going to happen next and updating your prediction all the time. I think that's far closer to a likely mechanism in the brain than perhaps back propagation, for example.
Okay.
So this is, look upon it not as look at more as a dialectic between AI and neuroscience. It works both ways here, but be very wary, as you rightly said there, of taking metaphors as truth. That would be a mistake.
Okay, let's move on to Demis Hassabis now, born 1976, starting to make us feel very old. A British entrepreneur, CEO, and sorry, I'll try and say that without a kind of British exceptionalism glow of pride. Or maybe I won't. A British entrepreneur, CNO and co-founder of DeepMind and Isomorphic Labs, and a UK government AI advisor. Maybe the education department ought to listen to him. Born in London to a Greek Cypriot father and a Chinese Singaporean mother. Hassabis was briefly homeschooled by his parents, bit of a theme there, during which time he bought a first computer, a ZX Spectrum 48K, and many of our listeners now will be getting very excited about that, the nerdier ones among us, which he funded from chess winnings. A very successful chess player, very young, and taught himself how to program from books. Remember them? Studied at Cambridge and UCL. In his early career, he was a video game AI programmer and designer and an expert player of board games. But given the context, that last bit hardly feels like hinterland. Games suddenly become very important in AI. Donald, I think most of our audience will have heard of DeepMind, but can you join the dots for us? How do we assess Hassabis' contribution to AI and, most importantly, to learning?
Yeah, well, Demis is a fascinating character, really. As you say, he was British. Geoff Hinton was also British born, but what's interesting about Demis is he does come from this rather odd background, as it were, and he's quite well known in the games world because he was the designer, conceptual guy and lead programmer of the very famous game Theme Park. Theme Park was a fascinating game because it had all this AI intelligence in it way back in the day. So, he was famous before all of this in the games world as a genius games designer and programmer. But what he does is something quite interesting. He goes off into academia.
Wow.
And he studies the hippocampus, this thing at the back of our brain, which is where episodic memory is consolidated. That what did I do in the pub type, almost like video recall of events from the previous night, previous day, or what did we do on New Year's evening. And he found that studies through brain damaged patients was one thing he looked at. It was caused by damage to this part of the brain called the hippocampus. Okay, and what happens when you have a damaged hippocampus is you not only lose memories, you lose your ability to plan and imagine the future. Now that's interesting. So you suddenly have this link between how we remember things and how we predict or imagine the future. It seems as though not that they're exactly one and the same thing, but they're certainly very close. This is an amazing, a fascinating insight in a way. He takes this idea, comes out academia after having written a couple of really important papers, and looks at this process of reinforcement in learning. Okay, you might call it just practice makes perfect. You know, how do you get to Carnegie Hall? Practice, practice, practice. You know, that's what really matters in the learning process. So he has this link between episodic memory and future imagination and creativity and thinking what could be the case. And he backs it up with all sorts of science. This is a guy who really knows the cognitive science and the neuroscience. And he comes up with this thing called scene construction. In other words, he thinks the brain, it's a bit like Roger Shank's script model. Not only for recalling memories, and so the brain, in a sense, is a sort of like a simulation engine. You know, it's like a little internal theater. We can imagine future scenarios. So he then applies this he then uses machine learning, which is well established in AI, and sets up a company in 2010. This is quite recently, 2010, called DeepMind. Okay. Now, what DeepMind focused on at the beginning was taking these really complex tasks, like beating somebody at chess or Go, and without any prior knowledge of training, and can beat that person. That's the key point. The AI can learn to do anything. So traditionally, the learning professional world saw human beings and animals as sometimes but inferior learners and teachers. Suddenly, we're a new kid in the block with bits of technology that can learn, bits of technology that can actually learn, and maybe they can actually teach. And I think that's certainly going to be the case. So the first system was a thing called Breakout. It not only got as good as any human, it actually, Breakout is a computer game. And this is how amazing this was when it happened. Breakout was so clever, it did something that no human had ever done before. It went round the edge and attacked from above. This is something that no human player had ever tried before, and of course could therefore beat any human player. So their system became more imaginative, more creative, more competent than any human who had ever played the game Breakout in history. That's why DeepMind managed to tackle things like chess. And I really would highly recommend that people look at the AlphaGo documentary on Netflix. It is an amazing film that shows the revelation during that process of how strong. I mean, during the games, it beat Lee Sedol, who was the world Go champion. It beat him 5-1 in South Korea and Seoul. That game at the time was a sort of holy grail in AI. You know, as I say, the number of possible moves, greater than the number of total atoms in the universe. They trained the model by playing loads of good amateurs, applied deep neural networks, things that they thought existed in the brain, and hey presto, it beats the world champion. AlphaFold. It then goes on to do an amazing thing. They have AlphaFold. That's a protein folding tool that predicts the 3D structure of proteins just from the amino acid sequences. This saves millions, if not billions, in research and lab time and money because you don't actually have to go into the lab to predict the protein structure. This is incredibly important, a foundational thing in cancer and many other areas of medical research. This is how fast this is developing now. Incidentally, they also reduced the energy bill in Google data centers by 40% using the same software. So it's starting. So the
bills down.
Yeah, people think AI is not having any effect in the world. You think again, guys, it's transforming the world. You know, and I think we should be proud that that came out of London, but it's one of the leading companies in the world. It is the beating heart of Google now, DeepMind. So all the way from Hebb, all the successors we've been talking about, we found out actually AI, using the techniques that were built slowly or surely over the 20th century, can suddenly be a very sophisticated learner, can start to be competent. Of course, this is competence without comprehension. It's not conscious in any way. It's not a human being in any way, but it can do the things that human beings can do, and sometimes a lot better. And in the learning sphere, I think this is important, which is why I wrote that book on AI and learning. We have to waken up here. This is now happening. And are we using it? No, we're still doing, text graphic, multiple choice question. It's plainly absurd that we're not using smart platforms, smart intelligent content, smart data to improve the learning world. Because we will. Resistance is futile. This is going to happen. Yeah. It's just that we seem to be ploughing the same old furrows.
You should say we're not using it yet, Donald. Growth mindset.
Yeah. Well, yeah. Okay. We have all sorts of bullshit, associated concepts and words with this. But to be fair, we're starting to use it because there are people like Learning Co. would be a good example of this. I think one of the best examples, who suddenly got the AI message, and applied it for real in their technology, and they do, all the training for some of the biggest, people like KFC and Taco Bell, with people with hundreds of thousands, if not millions, of employees, 250,000 who leave every month. These are now become big data problems, but they use that data in a very clever way to inform the content and the way those people are trained. I myself have been doing lots of, I invested in an adaptive learning company that was bought for cash by Cambridge University. And there's no way that teachers can do the sort of personalization and adaptation as people are vectoring through courses that software can. So that will happen. We now see content production actually happening, not only text production using ChatGPT, but also image production using DALL-E and a whole rack of other tools. We'll see video production. We'll see very sophisticated things happening in the learning field over the next few decades that will change that landscape forever. And I mean, make it better, faster, and cheaper. This is really important because who would deny that it's an esoteric system? That whole sort of Ivy League high-end university system is built on scarcity, keeping things away from people. It's not an open, democratic, decentralized system. It's an elitist, hierarchical system limited to the few, not the many. So I think we have a chance here, a glimpse at what may happen going forward.
I think we've moved there into the what we'd normally say was the kind of summing up section and looking forward. But I think you've nailed it there. And I think, just to keep this to a reasonable length, we've probably arrived at a good finish point here.
Sure.
So thank you very much for that, Donald. I've learned a huge amount. I should use verbs like learned fairly carefully, given some of the content of this series, but I feel as if I learned an awful lot today. And I hope the listeners have as well. So thanks a lot.
No problem. It's an interesting story, and one I think that should be recognized as an astounding, as you said, almost as important as the precursor period before Darwin. It really is that important.
Great Minds on Learning comes from the Learning Hack team and is produced by John Helmer. Sound edit is by Isaac Peacock. Social media by Jay Curtis. Graphics by David O'Connor. The podcast is based on a series of blog posts written by Donald Clark, and would like to thank Donald for his kind collaboration in this project. If you're a fan of these podcasts and want to support us and get exclusive member benefits, go to patreon.com/learninghack.